Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to MSR New England. And today we are more than happy to have Professor Ted Edelson from MIT to give us a talk on line shading and shape. And it is my greatest honor to introduce Ted. So Ted was my thesis advisor at MIT. I learned a great deal from him. And before talking about personal stuff, I want to first talk about his research work. So Ted has been really laying down the foundations for computer and human vision. And he has worked on three major areas, including multi-scale image representation, motion perception, especially layer motion representation, and also surface perception, which will be today's talk. The foundation that he laid in these three areas really leads to a lot of work in computer vision that spans very broadly from, let's say, image representation or multi-scale, like Gaussian Laplacian pyramid, a lot of pyramid representation for images, that leads to denoising and multi-scale image processing, and motion estimation, layer motion representation and estimation, and also material perception recognition. So that's really a broad area in the whole image processing and computer vision, computer graphics area. And really, although there's no paper about this work, I was really fascinated by Ted's checkable shadow illusion that he created in early 80s about human perception of brightness. And this is such a great example of the gap between what computer sees and how we see a picture. So here, if you look at area A and B, we would all agree that A is darker than B. Right? A is darker. A looks darker than B, or B is brighter than A. But the fact is, they have the same brightness. So they are actually equal. So the real RGB values or the real intensities of those two areas are exactly the same. But to us, they look very differently. And here is a concrete, it's a process of showing how, starting from the same areas, actually gradually becomes different to our eyes. And Ted has done a lot of work. This is just a very tiny piece of his tremendous amount of work on this perception. And I think really his specialty is really lies in bridging human perception and computer perception, computer vision, of building mathematical models for understanding images. So that just shows a tiny bit of his work and his influence to the field. And personally, I have learned a great deal from him. I think my view of research, how to do research, has changed a lot after being his student. And one thing I learned is really the purpose of doing research is not just to really publish papers, but rather to really understand the truth of this God-created world. And let's welcome Ted to give this. Okay.
All right. Is my mic working? Yes, you can hear me anyway. Thank you, sir. And I have to say, it's been a great pleasure to be able to say that So worked with me at MIT. I was his co-supervisor with Bill Freeman, and I couldn't. In fact, when So was interested in coming here, I said, well, don't come to work with me, but you could come to work with me and Bill. So that's what happened. And I would like to, last time I was here, I talked about material perception. And today I'm going to end up talking about shape perception, and as it says here, this is about how I failed to avoid working on shape perception, because that's not actually what I want to work on. But you'll understand why I ended up working on it. All right, so an image is a bunch of pixels. How did those pixels come about? Well, you can think about that as asking, well, suppose you're going to make a graphics model of this and render it. What do you need to know? Well, you need to know the optical properties of the material. You need to know its shape. You need to know the illumination, which is to say all the stuff around it, which is going to cast light on it, and where you're looking at it. So there's all these different sources of information that end up coming together in a complicated way to make this array of pixels. And the computer graphics problem is actually pretty straightforward. You're just doing, basically doing physics and trying to do it efficiently. And so that's how you go from the world to a picture. But the computer vision problem is, how do you go from the picture to a model of the world? That is, how do you look at those pixels and figure out what happened in the world that made them? Well, so this is why computer vision is taken so long, is because it's this inverse problem where there's no right answer, but because humans tend to agree on what something looks like, it makes sense to figure out how we can make computers do the same thing. And early on, a long time ago, I was struck by the fact that everybody in vision, both human vision and computer vision, they work on object recognition. It's a famous problem. Some people think that's all you should work on. But there's this other property of the world that's very important, which is material perception. So, you look at one of these chairs, you say, what is that? Well, it's a chair, but it's not enough to know it's a chair. The fact that it's a chair, it's made of cloth, it has a certain softness to it. The arms are made of plastic with a certain shininess. That's all the stuff that you take in is very important to you. Really important when you're eating food or when you're finding a mate. You like her hair or whatever. It's just a very if you look economically, if you open, in particular, if you open a women's magazine, you see what are the ads about. Most of them are about stuff. Most of them are about materials, like how to make your skin better, your hair better, your clothes better, whatever. So, but it's a neglected problem. And well, why haven't people worked on it? Well, because people don't know what to do. Because you've got something like this, it's a bunch of pixels. How can you possibly figure out all of these things at the same time? And so a while back, I was frustrated about this, and I also couldn't figure out what to do. So I said, well, let's get rid of shape. Let's just say, fine, we've got this complicated stuff, but we know the shape. We're going to make everything we look at be a sphere, and we'll know it's a sphere. And spheres are great because spheres always project to disks, and so all we have to worry about is that information, and we already know it came from a sphere. And you'll observe that this picture and this picture, they're both pictures of these shiny chrome-plated balls. They look very similar. They're both pictures of shiny chrome-plated balls, even though the pixels are all different. And likewise, on the left, okay, that's a black shiny ball. Again, the pixels are all different, but you can tell the materials are the same. And the pictures are different because the environment's different, and the environment has this big influence on what pixels you end up with. But our hope was, well, maybe we can, if we simplify the problem, we can do some simple stuff like gather some statistics, we run some filters over it, we look at the distribution of pixel values. Maybe we can take some measurements and figure out what the material is independent of the environment. Because that's kind of what you mean by material perception, is to say, well, this is the same material even though I'm seeing it in different conditions. And we did some work that was encouraging there if we restricted ourselves to spheres and we knew that it was spheres, so we simplified the problem. This idea of working on statistics, these were our statistics, in this case, on the outputs of filters, such as the like wavelet filters, or center surround filters, if you know the physiology of the visual system. And you can just look at, this is, what it actually did here is much more complicated than I can explain. But using a robust version of these filters, take a picture like this, and you can find negative outliers or positive outliers in these filter outputs. And they look very different. They're obviously carrying very different information. We know early on in the human visual system and in lots of machine vision systems, information is split this way. And usually people don't look at specifically look at positive or negative outliers. But if you do, you see that this information here just looks very different from that. And in fact, this stuff seems to be telling you about the shininess. So this is something, it's a simple operation we can do with filters. If we have Obama and we decrease the shininess information, we get that. If we increase it, we get that. And so just this very simple filter statistics lets us, by manipulating that, we can make Obama look shiny or less shiny. So that, it's encouraging that it must be telling us something about materials if we can manipulate the material appearance. But it's just turned out there's a real limit to how far you can get just by doing these kind of statistics, because the statistics are always take on meaning, not on their own, but in the context of shape. They're always, you've got these certain bright lines on these wrinkles or this bright spot on his nose. And so my wish to get rid of shape so as not to have to work on it is after all this time, I've just given up and concluded it's not possible. So what's the problem? Well, the first problem is I don't work on shape, on 3D shape. And in human vision and computer vision, people divide themselves into the sessions and the journals and whatever. They're divided, I work on this, I work on that. And I don't work on 3D shape. Other people do that. And they devote their lives to it. And I don't want to. All right? Because, I've got enough things to worry about. Someone else is supposed to be worrying about that. So, well, I'm a professor at MIT, and so the great thing is you can get a student and say, go implement some, shape algorithms, like shape from shading, and we'll take the output of the shape algorithm and we'll use it in our material perception. And so I have to learn how to shape. I can just build on these foundations other people have established. Well, it turns out that, to my surprise, that there are no good shape from image algorithms. That is, in spite of what you might have heard. So I've switched to plan B, is start working on 3D shape. All right, so when you say this, I thought, and most people think, well, shape from shading, for example, there's a very simplified toy version of a shape from image problem. That's been solved. Bertolt Horn, like 40 years ago, he did this seminal work on the case where you've got a Lambertian surface. That means a matte white surface, an ideal matte surface. You've got a Lambertian surface and a point source of light at some distance. The math is really simple, and you can work it out and get the surface normals and integrate it and get the shape. And under some conditions, you can do that. And so, and then, you know, in the 40 years since then, people have worked on improving on those results and making them more general. And and this is the problem, right? You've got that image and you want to turn it into a three-dimensional surface map, which is rendered here in 3D to show you. All right, so that's Horn, the original work. That was his thesis at MIT. Under the, by the way, his advisor was Marvin Minsky. All right, so then we've got a simple algorithm for shape from shading. We've got a robust shape from shading algorithm. We've got an optimal algorithm for shape from shading. It looks encouraging, right? We've already gotten to optimal. Although it took a long time. But you might think, in reading the literature, that people actually could do shape from shading. And every 5 years or so, somebody says, okay, I'm going to run I'm going to do a review article, and I'm going to implement all the algorithms, and I'm going to compare them and see which one is best. And it's ridiculous, because what happens is, one algorithm is bad, and then the next one is worse, and the next one is even worse. And the equations get longer and longer, and the clusters the computer clusters you need get bigger and bigger, but the results continue to be disappointing.
So how come the 140 years ago did so much better?
Well, on this particular image, it wouldn't do better. It was doing on. Berthold initially was working on things like the surface of the moon, where under the right conditions he could make it work.
Oh, he never did the picture you showed.
No. But anyway, so the fact is, this took me a long time to figure out, but shape from shading really just doesn't work very well. And I'm going to tell you about progress we've made on shape in general, but I can't claim that we've solved everything, but I will get to that. But anyway, the problem of shape from image has not been solved, even in very restricted cases. And oddly enough, there's this interesting problem as an academic, which is that if you submit a paper about shape from shading, or that's related to shape from shading, it's automatically rejected. One reviewer will tell you, this problem was solved long ago, and the other one will tell you, people have been trying to solve this for ages and no one ever has, and it'll never work. Anyway, so nobody wants to read shape from shading papers because they've seen so many of them and they've just gotten discouraged. All right. There's this variant. I don't think I'll just mention we made some progress in shape. This is with Chemo Johnson. Back, Woodham, who was I think a student of Berthold Horn's, did this nice idea. Well, shape from shading doesn't work. It's too ambiguous. But if you've got 3 different lights, for example, 3 different colors coming from different angles, then everything is disambiguated. You can get the surface normal beautifully, and you can reconstruct the shape. And it really does work, and people really do use it. The problem is normally you don't have the luxury of being able to set up 3 lights and calibrate everything and know what's going on. Recently, Chemo Johnson, working in my lab, just said, well, let's just consider natural scenes. Most of the time in a natural scene, actually, you've got different colors of light coming from different directions, but they're just different in a very subtle way. So here, in this example, you can see there's slightly different colors in the shadows. And it turns out only a little bit of color information is enough to sort of break the ambiguity and instability and make shape from shading work much better. Well, it's not really shape from shading. It's shape from shading with a little bit of help from the fact that you've got multiple directions, even though the colors are very weak. So even in a room like this, we've got one color. Actually, we've got halogens and fluorescent lights, and we've got the natural light coming in from there. And even that subtle amount of color is actually quite useful. And this just leads back to an interesting point, which is that even though we think that the way to think about vision in a simple way is to think about simple cases like Lambertian object, point source at a distance, the human visual system does not seem to feel that that's what it needs. So here's two renderings of a somewhat shiny green ball under two conditions. In one condition, on the left, there's a distant point source, just one. And on the right, it's in a environment like a room where there's multiple lights and objects that are reflecting off of it. And what you'll notice is the one on the left, although it's plausibly a shiny green ball, the one on the right is much more compelling. I hope there's enough. You can see that well. Yeah, I think so. The human visual system doesn't seem to want to work in these simplified situations. It likes working with the rich complexity of the real world. So that encourages us to think, well, maybe we should abandon this idea of trying to come up with a very simple toy problem where we can do the math, and instead look at the more the complicated problem that humans manage to deal with. Okay, so back to this picture. Is there hope? Well, so what do we have here? We've got this environment reflected in this surface, and that's all it is, because this is a shiny chrome object. It's just a picture of the world around it, except distorted in some way. And it could be any world, so how could you hope to extract anything with that? We want to find some properties that are stable across lighting environments and which are informative about the shape. So we can throw any old light environment at it and it'll work. And we want not just to do that for these environments, but also for the materials. So here on the left that's a Lambertian matte surface. And you can see the shape, no problem. And if you change materials, I'm not showing you here. Do I have an example of this? Oh, here's different materials. There's a metal version up there. There's a plastic version down there. You can see the shape in all of those cases. So there's this robustness of human perception, and maybe it's something extremely fancy and elaborate, but maybe it's not. Let's hope it's not. Here's an observation. This is based on work of Roland Fleming, who was a student in my lab. And what he observed is, all right, I've got this image here. Now suppose that I throw this into a shape from shading algorithm, a classical one with all the equations. And it's going to look at every point, and it wants to know the exact value because it's going to do all this math based on those exact values. And if I mess it up, like my camera doesn't reproduce the gray values exactly right, or I intentionally say I'm going to run each pixel value through some non-linearity that's going like this or like this, it'll mess up all the math and you won't be able to get the shape back. Of course, people can't get the shape back anyway, but surely if you mess up those numbers, it's going to totally screw it up. So suppose you did something really crazy, which is this is the input value of the pixel, and this is the output. So what happens is dark pixels are dark, light pixels are light, but in between, it goes up and then it goes down. It's actually going negative here, and then it goes back up again. It's this crazy lookup table, and it leads this thing to turn out like that, which is some funny, ghostly, I don't know what, it's not clear what it is. What material or environment could make that? Well, probably no material or environment could make that, because we just got it by running this thing through that thing. And so no shape from shading algorithm that's based on the equations of the real world is going to work, because there aren't any equations that would lead to this. But we look at it and we can see the shape. The shape's almost exactly the same. Maybe you might argue about it, but basically we see the shape no problem. So obviously we are not, our visual system is not agonizing about getting the intensity values at each point right to 3 decimal points. We are looking at something else. And in this case, you can just ask, what could there be in the image that does not change when I run every pixel through a lookup table? And the same lookup table. And the answer is the isophotes remain the same. So the isophotes, if you think of an image as a, think of intensity as a z, you've got x, y, and intensity. The image is a surface, right? It's high where it's bright, it's low where it's dim. And the isophotes, that just means the iso height contours, right? So you can look at all the pixels that have exactly the same value. They will follow some contour. Darker ones will be some contour. You get a bunch of contours on this tracking the same value. And if you run it through this lookup table, what happens to those contours? Well, they don't move because the same value in is the same value out. So even though you've wrecked everything, those isophote contours aren't changed. So, so that's something that's stable. And if you're basically, what you're saying is, look, there's change. We've got some isophote contour going this way. That means nothing is changing in this direction along the contour, and all the change is happening across the contour, wherever the contour is. And so you've got this directionality to this image, which is preserved. What is the direction of maximum change? Which is the sort of thing you can get by running filters over this and extracting local orientation information. What is the direction of the gradient, basically? And you can do those computations, and this is from work with Roland Fleming and Antonio Torralba. And what we've done here is coded the orientation, the direction of change in color. So color is a circular variable. So the intensity of the color is the strength of the luminance gradient, and the hue itself, what color it is tells you about the direction. So just to say, this picture has that pattern of local orientations. This picture has that pattern of local orientations. They're almost the same, even though the pictures are totally different.
It's also stable if you change the lighting?
Let's see. Good question. Happens to be the next slide. What happens if you change the lighting? Amazingly, it's still stable. And stable is a relative thing, so it's not perfectly the same. But you would think, so this picture is taken in a forest where all the trees are vertical. And I don't remember what this picture is taken in, some other environment. Obviously, if you're in an environment and it's got some shape and it's got some orientation and directionality, that's going to have an impact on what ends up in this picture. But it turns out just the overwhelming, the impact of the object itself is really so overwhelming that it tends to overpower that. And so here, right, what you can see, we've got this thing. It goes up like this and it goes down. It's going in a dip. And you've got this ring around it where all the orientations line up around that ring, regardless of what's out in the world. Happens again here. All the orientations line up around that ring. So, it is possible to construct environments where you've intentionally made things so extreme that you start getting into problems. But in natural environments, it just tends to be that these things are surprisingly stable. And all right, so that is the observation, and I'll take you on a slight digression here. Because this observation ended up taking my research to another topic, which is how do you draw lines to make realistic pictures? How did we get there? Well, line drawings are interesting because they convey shape without conveying material or illumination. They just tell you shape. I mean, that's the artist's intention. Right, you know, the nose, you can see the nose is sticking out. Of course, you know what noses look like. This is a cube with surrounded edges. This is a field. There's this field called non-photorealistic rendering in graphics that has become very popular in the last 15 years or so. And it's a change from the way things have been because, let's see, historically, what was computer graphics, almost always the goal of computer graphics was to make the computer give you something that looked real. And so that means setting up a lighting environment, an object shape, material, and running it and getting this stuff out. That's now referred to as a special part of graphics called photorealistic rendering. And of course, you can make a rounded cube with photorealistic rendering. The only problem is you have to choose some material and some environment in order to do it. And line drawings are kind of cool because, first of all, it's just amazing because they don't look like images, and they have this purity that they are just telling you about the shape. And the problem has, for a long time, the problem in computer graphics was, where do you draw the lines? It sounds easy. But you've got this object in your computer's head. It's a three-dimensional object. You want to make a picture of it on the screen, two-dimensional picture, and you've decided, I want to make it a line drawing. How do you go from the 3D object to the line drawing? That turns out to be a harder problem than you would think. There are two techniques that are pretty good. Let's see, I just took you through this. One's from, this is, the first good work was from DiCarlo's lab, and then we added something to that. This is work with Tilkejad and Fredo Durand. Their thing is called suggestive contours, ours apparent ridges. Our inspiration was to say, look, you know, we have this observation that at these points, you tend to have changes in the brightness. Now, it might be going from dark to light, it might be going light to dark. Where does that happen? When do you have this directionality changing this way, not that way? Well, the answer is if you've got the surface normal going like this, and the faster it's going, the faster the change is. Might be going up, might be going down, might be going up and down, depending on what it's looking at in the environment, right? Might be going up or down. But there are these points where there's, because of the shape, regardless of the environment, because of the shape, there are these points where you're going to tend to see isotopes lining up, you're going to tend to see change. And if you take this rule, take a shape here in the computer, and you say, suppose I'm looking at this shape, where are the surface normals changing quickly? Now, that has to be taking into account foreshortening, because that foreshortening meaning basically the projection. But if you just ask that question, where are they changing quickly, and draw a line at those points, you get this kind of a picture. So that's nice. We have these observations in two directions. One is that if we have a shape, then the direction of these locations and orientations tend to be stable. And then sort of conversely, if we do a line drawing and we put lines there to indicate where those things are, we convey the shape. And so there's this nice sort of reinforcement of computer graphics and this sort of this human vision and the computer vision. And the problem is we still haven't figured out to do what we really want to do, which is look at a picture and get the shape. All right, so that's where we are now. That's something I and my colleagues are working on now. And that is, let's look at a picture and get the shape. This, I'm going to describe very briefly this work we call Shape Collage. This is work that's, I guess I think I have to go to the next slide. I mean, I've got that on a separate presentation. This is work in collaboration with Forrester Cole, who was a postdoc, and Bill Freeman and Fredo Durand, and Phillip Isola, who is there, who's interning here this summer. So, and who can tell you about this much more accurately than I can, since he has actually been deeply involved in it. And this will appear in ECCV, a European Conference on Computer Vision, even though it has shape from shading information in it, and therefore was rejected from the previous conference we sent it to, even though we're working on a problem that's already been solved, or can't be solved. All right, so unified approach to estimating shape from images. Can we get shape from images? Can we find information in images that is consistent and stable enough across conditions that we can use it to estimate the shape? And what we're going to do is, basically in computer vision, there's sort of two different approaches, styles, schools of thought. I mean, there are different, people do them both. But there's these parametric and non-parametric approaches to vision. Parametric meaning, basically, you've got a description of the object that's got some nice math in it, and you try to figure out how that's going to turn into nice math in the image and try to figure all that out. Non-parametric meaning you've just given up on the math, and you're going to just look at lots and lots of examples and say, I don't know what the physics is or how it's working, but I know I've seen lots of things like this before, and so based on what I've seen before, I'll try to figure out what I'm seeing now. Anyway, so that's what we do. We're doing is the giving up on being smart and letting the computer be smart instead, and hoping that when the computer is done being smart, it will tell us what it did that was so smart. Anyway, so it's a learning-based system. As I said, the key thing is we do not want to make these very restrictive assumptions about the material or the lighting. So we're looking for cues that are going to be robust, cue information. And we'd like it to work with these real-world pictures, photorealistic renderings, and also stuff like line drawings, which looks three-dimensional to humans. So basically, if people look at it and see shape, we would like our computer to look at it and see shape too. And again, there's this long history in shape perception and perception in general of people dividing up. Not only did they divide up in shape perception, but within shape perception. There would be people who work on shape from shading, this stuff where you've got this continuous valued shading function. And there are people who work on shape from texture, like this, where you've got some pattern over the thing. And there are people, not very many anymore, who work on shape from line drawings. And these have been different people who publish and review each other's papers. And you get a shape from texture person, you paper, you send it to a shape from texture person. And therefore, the assumption has been, well, in the human brain, there must be different, there's a mechanism for shape from shading, and a mechanism for shape from texture, a mechanism for interpreting line drawings. And in your computer, you're also going to have these specialized systems for each of these things. Sounds reasonable, but what we are hoping we can do is do them all at the same time. So we just have one box that we're going to throw all this stuff at, and it's going to do everything. So here's a rendered image, and we want to get the shape. You have to define what you mean by shape, and what we mean is surface normal. There's at every point we would like to know the surface normal. We regard that as a demonstration of successfully seeing the shape. You can argue about that, but what this allows us to do is do training, because we can synthesize these images. This is the shape. There's the map of surface normals in the computer, and this is the set of intensities that came out when you rendered it. And they're in register. We can lay them on top of each other, and so we can say what the right answer is at every point. And so that means two things. We can train. We can give the computer lots of examples where we know what the right answer is. And we can test by giving it a new example it's never seen and seeing if it can get the right answer. And again, what we would like is to be able to just throw all this stuff at it and have it come back with this shape. All right, and another problem in getting this published, I have to say, is that the list of buzzwords in our paper is very similar to the list of buzzwords in other papers. And it's got exemplar-based or patch-based learning. It's got Markov random fields. It's got all this. It's got all this stuff that all different people also have. And so, so we're working on a problem that's old and boring, and we're using these techniques that are old and boring. So why would anyone publish it? And the answer is because we actually got it to work, and on this interesting set of inputs, and that involved a lot of work and thought, mostly by Forrester and Phillip, in going from the buzzwords and figuring out how to actually do the implementation. And I'm not going to have time enough to tell you details about what it is that makes it work. As I say at the bottom, the devil is in the details. But the basic idea is, again, something that's been around for a while, Bill Freeman being one of the people who pioneered it, which is this. All right, here's a bunch of images of shapes. These were rendered from shapes. And for each one, I'm going to look at patches on that shape, on that image, find an interesting patch, and remember it. I'm going to stick it in this dictionary of examples. And because I made it, because I synthesized it myself, I know what the underlying surface normals were there, so I record that too. So I've got this pair. I've got this little patch of shape, and I've got this little patch of, I've got this little patch of an image and a little patch of shape in the world, and they go together. And so I can get lots of examples like that. And build up this dictionary that's just my memory of every patch I've ever seen, and what the shape was when I saw that patch. And the problem with this is, the problem with saying this is it sounds good, but actually doing it in a way that is feasible is quite difficult. You have to choose the patches well. You have to distill the information in your dictionary. And you also have to combine the information well. But here's an example of what you do. You or the computer is looking at this image, trying to figure out, you've never seen this image before, and you're trying to figure out what is the shape that made this image. So you look at this patch, you say, well, let me start simply. What is the shape that made this patch? Have I ever seen a patch that looked like that before? And I go into my dictionary and I say, yeah, for example, I saw that patch. And what was its shape? Well, that's what its shape was. So for every patch, I've got examples of shapes that made something similar to, not exactly like, but similar to that patch. So I go around and I find, at every point I say, what's my best guess about what's going on here based on what I'm seeing? And and life would be easy if you could just do that locally. Just say best guess here, best guess here. Maybe you take the mean or some other way. Look at all the shapes that correspond to that patch and locally make a guess. But it turns out you can't do that, and that's true in vision in general. You can't. If you could, it would be really simple if you could just do things locally. But it turns out everybody basically has to agree with each other. That you have to agree with your neighbors, and everything has to come together and form a coherent whole where not only does this image plausibly come from this local shape, but it plausibly is next to this other local shape, and so on. So there are these techniques, again, belief propagation, etc., that people use to enforce this idea, which is I've got all this local information, but which is ambiguous, so I want to combine it globally so it forms a coherent whole where everything is locally plausible and it fits together in a nice coherent way. And there's just something about the ambiguities. I'll skip that. Well, I think I've basically told you the idea. These are the details which are crucially important, but which I've said so much stuff that probably there's no point in saying all the details right now. We do it multi-scale, so you've got small patches and big patches. We keep the sort of the dimensionality of the problem reasonably low by having this sparse graph of connections rather than having everything connected to everything. We've got big stuff and small stuff, and we got to try to take as few examples as possible, sparsely distributed. And we can get back stuff like this. So here's a bunch of training images, 6 different rendering styles. We trained all at the same time. We didn't tell this thing anything about line drawings or shape or texture. We just said, here's a bunch of images, and I'm going to show you, here's an image, here's the shape that made that image. So these are all made from this, each row made from the same shape. And now, let's put it to the test. So we've got this ground truth. We've got a new picture that, we got a new shape that the system has never seen before, and we're going to render it in various ways and see if it can figure out what the shape is. So one thing, we'll take this shape, that's the shape. We'll make a line drawing using these computer graphic techniques. There it is. We'll also render it with Lambertian shading, like this. We'll also put a texture on it, like this. Texture here looks kind of weird due to some artifacts. And we'll see, can it get the answer? And the answer, the answer is, well, yeah, pretty well. It's not perfect. We still have work to do. But we're getting reasonable, qualitatively correct answers from all of these different techniques, all from one system. We do not have specialized systems for each of these, for lines and for shading and for texture and so on. So, I guess the one thing I should have said is that part of the big problems is, what do you mean by similar, right? I've got this image patch. It's similar to other image patches. It's very important that that similarity metric be based on this distribution of orientations, which we found to be so diagnostic of shape. And that's a crucial part of what makes it work. Anyway, this is, I think, very exciting work. It's work in progress. We obviously have to extend it to more complicated shapes and real-world scenes, but we're very encouraged by the fact that finally we've got something that has a chance of working with the diversity and richness of information that you get in the real world. Okay, so just to summarize that, we are learning this mapping from local patches to local shapes. We use various techniques to enforce compatibility, coherence across the entire image. We get a bunch of patches. We then fit a smooth spline to the patches to get the estimated shape. All right, as I said, there's much to be done, but we're excited to be here. And getting back to human vision, and unfortunately, at this point, I'm not going to be able to get back to material perception, the thing that was driving it from the beginning. But just to explain, what could this tell us about human vision? And the first thing is, sometimes when I describe this, people think that I'm claiming that humans learn to see shape this way. That humans, that they see a patch of a shape and they feel it, figure out what its shape is, and they learn that patch. We're not making any claim about learning or development in humans. We are just asking, we're building a computer vision model with the goal of making something that can see shape. And that's so hard to do that we figure that if we can make a computer do it, and it has the same kind of robustness that human vision has, that maybe we've captured something that humans also have captured somehow. We use SIFT, that's the thing that gives us orientation. It's nice, robust, and flexible, blah, blah, blah. Things I've just said, I say here again. And I think I can stop at this point and just say thank you for joining me on this sort of travel log of how I started in material, trying not to do shape and ended up working on shape. And what I've liked about it is the fact that we've been able to combine stuff from human vision, from computer graphics and computer vision to sort of converge on these ideas, which seem to be working pretty well. So thank you very much. Yes.
For your talk. I'm really fascinated by your last statement there, because I'm thinking back to the green ball.
Yeah.
And I'll save you the trauma of what I was thinking about it. But the comment about that you proposed there's a unified system, I feel like so much of your argument early on was that thinking about texture and lighting and all the environmental factors that are shaping what I see as a shape. So in terms of vision, that seems like the disparate systems that seem critical to interpreting what I see. So why would you make a claim that you feel like there's a unified system of human vision to be found in the thick of that, if I'm understanding what you're posing?
So if I understand what you're saying, at the very beginning I said, look, you've got the shape of this thing, you've got the environment around it, you've got the material and how it reflects the light, and those are all getting mashed together in some complicated way. And that's still true. I'm not claiming that that's not true. That diversity of sources of information remains there. What we're hoping is that we can look at each of those things and not have to solve everything at the same time. And one of the sub pieces of that puzzle that we're trying to make progress on in in the second part of this talk is shape. We say let's just try to work on shape. Let's try to find information about shape that's going to be useful information, even if I change the material, even if I change the lighting. It's not. I don't want to claim those things aren't important. They are very important, and they remain distinct kinds of information that we still want. I still want to be able to look at the thing. You know, this is always a problem when you're building a vision system. You say, well, let's look at these chairs. My goal is, if I'm doing object recognition in the classic way, my goal is to take that chair and replace it with this label that says chair. And, well, but that's not really my goal for a vision system, because I want to be able to go and sit on that chair and make a guess as to what it's going to feel like and so on. So on the one hand, you're trying to, when you do vision, you're trying to throw everything away and sort of just get one thing and get rid of all this other stuff. But on the other hand, you also have to keep all that other stuff. So I agree with you on the importance. I don't want to say we want to mush everything together. We do have to keep those things separate. We're trying to work on one at a time. Yeah.
From evolution perspective, I don't know, I'm not a biologist, but it seems that it wouldn't make sense that we would develop a separate system to interpret line drawings, right?
I agree. Why would there be a line drawing system built in? And this is one of the puzzles. And people have proposed, there's actually, is it here? No, it'll be too hard for me to find it. People have various proposals, like line drawings. Here's an idea that some people have said, well, line drawings, what are they? They're these very sparse representations of the scene which extract information that's important, like information about the intrinsic geometry of the surface. That seems plausible. And maybe what happens is the line drawings kind of jumps past all this stupid vision stuff at the beginning and goes right to the brain and says, there's something interesting, important happening here. Well, we don't think that's true. We think humans, as you say, they evolved to use their eyes to see objects that are rendered in light. They're designed to deal with the pixel values. And the line drawings, there happen to be a nice representation which manages to convey, using what we already have, manage to convey the shape. Yes?
Is there a consideration of like a trade-off between the speed and the accuracy?
In our algorithm, well, yeah. Everybody's algorithm always needs a little bit more computational power and a little bit more memory in order to work. And it will work better if you give it more. We haven't tried to, our goal at this point has just been to get it to work, and we haven't tried to look at the trade-off between speed and accuracy. It's fast enough for a publication. It's not fast enough for a robot. Yes?
How did you decide on the unit for a lookup within the dictionary? If that makes sense of the question.
Ask the question again.
How did you decide what the unit that you would store in the dictionary would be?
Oh, so so Philip can answer this better than I can, but I will try. You could, in principle, you could take any old patch just randomly and say, I like that patch, I'm going to store it. But there's lots and lots of patches that are just boring because they're blank. And there's also lots of patches that look just, you get too many of them because they happen a lot. And there's patches that are too complicated because they include the entire image or something. And so a lot of the details that make the thing work was various considerations in that exact problem. How do you choose which patches are worth keeping? And the answer is we try to choose patches that are in what we consider to be important places, which are places with strong orientation. And we like our patches to be small enough that they're not looking at something very complicated, like here if you had a patch that contained this entire thing, it would be complicated, so complicated that you would never ever find another patch that looked like it. So that's a vague answer, but it's that kind of consideration. Yes.
So when you said you define neighborhood or nearness by the contour lines, you could also have defined nearness by the ground truths.
Let's see.
By sort of saying I define them to be two patches near if the directional vectors are near.
Yeah, I'm trying to think, maybe can you do that for, I'll ask Philip. Maybe, it's possible you could do that during the building the dictionary part. And it's not what you would do when using the dictionary, because when you're using the dictionary, what you're given is an image, and you don't know anything about the surface normals.
But when you patch the images together, then you could again use the ground truths and say, the normals align correctly.
Oh, yes. No, I'm sorry. That is exactly what we do. We don't want to just find patches that agree in terms of the image. We want them to agree in terms of the shape. So neighbors should have surface normals that join up correctly. And and what you can have is, let's say there might be two interpretations of this point, one like this and one like this. And in terms of the image, they're both perfectly good, but in terms of agreeing with their neighbor, this one is much better than that one. So that is, I'm sorry, I didn't make that clear. That is what we do, is once we've got the hypotheses, we try to find hypotheses that agree in the shape space, in the ground truth space, rather than in the image space. Does that sound right, Philip? At least 80% right?
Yeah.
All right. Yes.
Since the dictionary is made of images which are all synthesized, then at least for this case where it's all synthesized, you could have, instead of using a dictionary that was pre-built, to just try to synthesize a patch which is the most similar to the patch that you're seeing on the go.
Right. And people have, not for this problem, people have built systems like that where they encounter something and then they try to imagine, basically, in the computer, lots and lots of hypotheses about how it might have come about. Sort of do training on it as they need to. I think that would be difficult here because we would have to synthesize an awful lot. For a given patch, we'd have to synthesize a lot of examples. I guess the advantage is we don't have to store as big a dictionary. And again, well, we should look at that, but that's not what we do right now.
So I have a question or comment. So I feel the traditional shape from shading and this new approach, actually they're complementary to each other. Because the traditional shape from shading is actually you have an energy function that you know your target. And you try to make a shape to fit into your target, right? So you have the physics, everything right down, and you want to synthesize a shape such that given all the lighting conditions, well, the shape the image that corresponds to the shape will going to look similar to the input image. But here you are taking a very different mechanism. It's basically we're guessing what the shape looks like from local image features, right? However, the image feature is computed from a contour, from line drawings, or from textures, from shadings. But I feel these two actually can be combined in a way that you can generate hypotheses from local image features, and you can verify that through the traditional approach. Do you have any comments on that?
So you're saying we could do a synthesis, a rendering step at the end, and see whether we got it plausibly right, which would work for something. It wouldn't work for texture because that's stochastic, but it would work for the shading and the line drawings. And I think at this point, I should actually ask Philip to say something, because I know that it's something he's thought about.
Yeah, I think that'd be interesting. Just use this as kind of an initialization for another optimization routine, and then maybe iterate. But I haven't tried it. We could try it.
All right, so it's a good idea. And also, it seems possible to me that you could say that classical shape from shading is similar to our technique, except the patch size has gone to 1 pixel. And the 1 pixel gives you a little information about shape. I mean, of course, classically it's not done with a dictionary, but 1 pixel gives you a little constraint on shape, and then you try to propagate these constraints around. And the problem with classical shape from shading is that that's just not enough information at a pixel. I don't know if we could literally I don't know if we can literally say our system is the same as shape from shading, is a kind of shape from shading with a patch size of 1 pixel. But we do have we do have local constraints, and we do try to combine them in a coherent way that has a lot of similar flavor.
Well, let's thank the speaker again.